It's fun to solve problems with moments on not necessarily on a seesaw. So this is an example of something that looks a bit like a roundabout. You've got lots of forces acting, and it's whether or not the blobby thing that's a bit like a fried egg is going to rotate around the origin, around this point here. So if it did, would it rotate clockwise or anti-clockwise? Let's have a look. Well, this 10 Newton force, that would rotate it in the clockwise direction. So would this 20 Newton force. So would this 40 Newton force. The 1000 Newton force wouldn't do anything because the line of action of the 1000 Newton force is through the pivot. So the distance from the pivot to the line of action is 0, so there's no moment. Then on the other hand, we've got trying to rotate the fried egg anti-clockwise, we've got this 100 Newton force here. So let's see what happens overall. So we've got 100 newtons times 4 metres, that's the moment on that side. And on the other side, we've got 20 newtons, that's a perpendicular distance, the line of action of this force here. This is a perpendicular distance of 5 metres to the point we're seeing if it rotates around, or the extent to which it rotates around. So that's 5 perpendicular to this line of action. And what else have we got? We've got 10, and the line of action of that force is 2 metres away from the pivot. And we've also got 40, and the line of action of that force is 3 metres, perpendicular 3 metres away. So altogether, if we take it, instead of, actually it's a big lie what I've just written here, no one told me that the fried egg is in equilibrium. I've just completely made that up, look. This says that it's in equilibrium and it isn't. What I should be doing here is taking these clockwise ones as positive and taking the anti-clockwise one as negative. And so let's get rid of that equal sign there and change it into a minus. And this will be the overall moment. This will be the net moment. So we'll be able to find out what's going on with the fried egg. So clockwise positive, anti-clockwise negative, all together we get, using calculator, or I make it minus 160. Not Newton seconds, that's impulse, Newton meters. Minus 160 Newton meters. So what that means is that the negative has won. Even though there are 3 forces trying to rotate the fried egg clockwise, the anti-clockwise rotation has actually won. It's quite far away and quite big, so it makes sense that it would win. So this is 160 Newton meters anti-clockwise. That would be the moment about the origin. Right, what have we got going on here? We've got a lamina, which is like a piece of paper, you can imagine it like that. And we've got a force acting at a point A, where A has position vector, so this is going to be the origin, and the position vector is 2i plus 3j. So this is 2 across, 3 up, this is the point A. And a force, 3i minus 2j, is acting at the point A. So it's going across 3 down 2, like this, and this is the force. This is the line of action of the force, like that. That's the line of action of the force, and there's the force acting through the point A. What else is happening? Another force is acting at B. B is at 3i minus 2j, so 3i and then minus 2j, here's B, that's 2, that's 3, there's B, and the force that is going through there is, what does it say, force 4i plus 3j, so it's across 4, up 3, there's the force, and there's the line of action of the force, like that, and this is what's going on. Okay. We want to find the sum of the moments about the origin and also about the point with position vector 4i minus 3j. So let's do the origin first and see how we get on. So what we need to do, you can see that the red one is going to try to rotate the lamina or fried egg, however you want to imagine it. Here it is. The red one is going to try to rotate that clockwise and the blue one anti-clockwise. And so the sum of the moments, or the net moment, will equal the red one, and that will be the magnitude times the distance, and that one's going clockwise, and then minus, and then the blue one, and that will be the force times the distance. Now, how are we going to find these things? Well, this force acting at A, it's got a length, a magnitude, given that it's going across 3 and down 2, it's got a magnitude of 3 squared plus 2 squared square rooted. It's just the length of the vector, which is 9 plus 4, root 13. So the magnitude is root 13. What about the distance? Now, we need the perpendicular distance. That's the thing. We need this distance here. And this is actually something that's really difficult to work out. But there is a little trick we can do. So what we're going to do is we're going to break up the force, the red force, into its horizontal and vertical components. So I'm going to have this one and this one instead of the diagonal. And I'm going to treat them as two separate forces, and both of them would try to rotate the fried egg clockwise about the origin. And I'm just going to break it up into those two, that one and that one, instead of the red one, instead of the root 13 diagonal. So this is going to be much easier. Okay, what is the magnitude of this force here? Obviously it is 3, because it's 3 across, so that's easy. What about the perpendicular distance of the line of action? Here's the line of action. So now this is really easy now. This is my perpendicular distance, but I know that's 3, because I know where A is. A is at the point 2i plus 3j, so this is 3. So this is really, really easy. No complications here at all. Okay, what about the other component, this one here? Well, obviously it's got a magnitude of 2, that's not difficult. So because it's going 3i minus 2j, this is 2. So this is 2. What about that perpendicular distance? Again, really easy. If you look at the line of action of the 2, then all we're asking is, how far is this across here? Well, A is at the point 2i plus 3j, so this is 2 across here. Then it's going another 3 across from here. This is the line of action. So in total, all the way across here is 5. Easy peasy. We didn't even need to do Pythagoras. Hooray. Let's do the same thing with the blue. So across 4 and up 3 instead of diagonal. Here's the line of action of the 4. So I'll put that one in. We've got 4 times, what's this distance here? Perpendicular distance to the line of action. That's that 2 there that I drew on, taking me to the point B. So this is 2. And the other bit is 3. This one here, this has got a magnitude of 3. What about the perpendicular distance to the line of action? There's the line of action. So what I'm trying to work out is how far is it from here over to here. But this one here is 3. Then there's another 4 across here. So altogether that's 7. Okay. So this is a much, much easier way of doing it, is to break them up into their horizontal and vertical components. So what is the sum of the moments? See if I can give myself, or I'll just do it up here. Sum of the moments equals, the red ones was 3 times 3 and 2 times 5. And we're taking them to be positive because they create a clockwise rotation. Both the blue ones would create an anti-clockwise rotation, so they're going to be negative. So that would be minus 21 minus 8. Altogether giving us minus 10. So this is a moment which is 10 Newton meters anti-clockwise. Let's see if we can work out what's going on if we take moments about a different point. So this can be the origin. So A is at the point 2i plus 3j. So that's 2 across and 3 up, and there is A. And through A, we've got a force 3i minus 2j, which we're going to split into its 3i bit, and it's minus 2j? Yes, minus 2j. Like that. Then we've also got B. B is at the point 3i minus 2j, So that is, let me just put that 2 there. Okay, so we're going 3i minus 2j, 3 across, 2 down. That gets us at B. And the B has got its force acting through B, which is 4i plus 3j. So that is 4 across and 3 up, like this. Now the point that we're taking moments about in this case is the point 4i minus 3j. Now where is 4i minus 3j? Well, this is across 2, then this is across 3, so this gets us to 3. If we go, this is 3 and this is 2, so actually this line of action, that's 5 away, so 4 is probably about here. So 4 across, and calculate some of the moments about the point 4i minus 3j, so we'll go 3 down, like this, and we end up here at the point x, I'll call it, and we're taking moments about this point. Okay, let's have a look at what each of these forces are doing. We've basically got 4 to consider, both the red ones and both the blue ones. Let's do blue first. Now the line of action of this blue force with magnitude 4, that would turn it, the fried egg, around the point x, it would turn it clockwise. What about the other blue force, like this? That would turn around the point x, if we pushed in that direction through that point, that would be anti-clockwise. What about the red ones? Well, this 3, this line of action, if we did that, that would turn it clockwise. And this one here, this red one, this would turn it clockwise as well. So we've got 3 clockwise, they're going to be positive, and 1 anti-clockwise. Let's see what happens all together, the sum. So red ones, we've got the 3 times the perpendicular distance, also positive because it's clockwise. We've got the 2 times the perpendicular distance, and then the blue ones, still positive because it's going to be clockwise, is the 4 times the perpendicular distance, but negative the 3 times the perpendicular distance, because that one's going to try to rotate it anti-clockwise around x. Let's put the distances in. So this one here, 4, what is the distance of this line of action from this point? Well, to get to this one we went down 2, to get to this one we went down 3, so this must be 1. What about the other blue one? We've got this line of action here, and how did we get, so it's across 4 to get to here, and then it is across 2 and across another 4. So across, what was I doing? Yeah, across 4 would get us to here, and across 3 gets us to here, and then across 4. So it's 3 add 4 is the distance from here to here, that's 7, and from here to here is 4, so from here to here must be 3. That's 3. And the red ones are the 3 here. The distance of that from here is, well, we've got this 3 and also this 3, so that's a total of 6. And finally, the last one, we need the perpendicular distance from this line of action to x, which is just 1, because this is 4 across, and this is 5, the 2 and the 3, so that's 1. So, adding it all up, the sum comes to 15, and that is positive. So it'll be 15 Newton meters clockwise rotation.